Let's do problem 9.46 of Sonntag, in which we have an industrial process which requires 0.5 kg per second supply of compressed air at 500 kilopascal. Okay, so the compressed supply has to be at this particular specification. The air is supplied by installing a compressor and an aftercooler. So there is a compressor which is fed into an aftercooler, and this is then fed as a supply. So the supply is, let me call this as 1, 2 and 3. State 3 is at 500 kilopascal and 30 degrees Celsius. Okay. The local ambient conditions are, so state 1 is at 100 kilopascal, 20 degrees Celsius. Okay, using a reversible compressor. So this is a reversible, and if it is an ideal compressor, we can assume it to be adiabatic. So this will be isentropic. The mass flow is at 0.5 kg per second. You must find out the rate of heat rejection in the aftercooler as well. Okay. So in the aftercooler, the pressure remains constant. Okay. In the so the process 1 to 2, it goes from 100 kilopascal, 20 degrees Celsius, to a state 2 where S2 is equal to S1. Process 2 to 3 is an aftercooler in which it goes from state S2 to state 500 kilopascal and 30 degrees Celsius. Usually in these coolers, there is a piping in which the pressure loss is negligible, so this state will be 500 kilopascal. Because this state is 500 kilopascal, this state also has to be 500 kilopascal. Okay, thus what do we have? Okay, so we need the work into the compressor. So if we assume a steady state steady flow process, so 0 equal to Q plus H1 minus H2 plus W minus W. Keep making this mistake. Minus W. So W is equal to H1 minus H2. So the W compressor is equal to this. This will turn out to be negative, and then we have to report it as positive because that is the work input of the compressor. The work done by the process is negative, which means the work input is positive. Okay, the heat rejection in the aftercooler, so 0 equal to Q aftercooler plus H2 minus H3. There is no work done in the aftercooler. Therefore, Q aftercooler is equal to H3 minus H2. That's it. Let's see what do we obtain. So this is problem 9.46. T1 is at 100 kilopascal, T1 is at 20 degrees Celsius, P2 is 500 kilopascal, S2 is equal to S1, S1 is equal to entropy, steam T equal to T1, P equal to P1. Okay, P3 is equal to 500 and T3 is equal to 30. Okay, so W compressor is equal to H1 minus H2, Q after cooler equal to H3 minus H2. H3 enthalpy of steam T equal to T3, P equal to P3, and H2 is equal to enthalpy of steam at P equal to P2 and S equal to S2. H1 equal to enthalpy of steam T equal to T1, P equal to P1. Okay, let's see what do we obtain. The work input to the compressor. We have multiplied to we have forgotten to multiply by the mass flux. Okay, that's the most common mistake. So obviously these are all specific quantities. In terms of actual quantities, these equations will be q dot plus m dot hi minus m dot he minus w dot and so on. So I've divided everything by m dot to arrive at these equations. So I must multiply everything by the mass flux. So this is equal to m dot multiplied by this. This is equal to m dot multiplied by this, where m dot equal to 0.5 kg per second. So let's see. So the work input to the compressor is 0.2 kilowatt. The heat exchanged is 20.9 kilowatt.